Welcome to the course this evening. So we had a break last Wednesday, which I hope you all enjoyed. So we are going to pick up where we last left off. Now there's a few things I sort of want to point out before we begin. So the first one is if you want to maybe follow along with this class and you haven't done your full massing model, so essentially you haven't followed up to the current point on your own site. If you open the syllabus, assignments, island model, and lots link folder, the Rhino 6 file, I've sort of got rid of it just for the moment. You can all open the Rhino 5 file, and essentially when you open that Rhino 5 file, you can also open Rhino 6, of course. You're just going to have the material to work with. So in here you can see that not only do I have a preview of the shape of things to come that we're going to do today, but also there is the kind of final massing that I ended up with the other class. So this is the massing model that we built based on that solar envelope. So there's that. So again, if you want to follow along, your massing model is not to this stage. That's okay. Just open the Rhino file in the Dropbox and you can follow along with this file. The second thing I want to say is, as per the email I sent out this last weekend, the second half of this lecture is going to use the plugin Octopus. So if you just go to Food for Rhino and look up Octopus, and if you download the second newest version of Octopus, so it's loading right now, I think it's version 3.4 or something, and anyways, that is going to be the one you're going to use. Here, wait a second, I'm just going to disconnect from my VPN. Okay, so, okay, so I'm back. Sorry, I just needed to disconnect from my VPN, so I didn't have legs in the video feed. So, essentially, you can download the Octopus 0.3.6. It's going to be the same as the newest version of Octopus, more or less. Essentially, I'm just choosing this version because it'll work for those of you with Rhino 5 instead of Rhino 6. On the topic of Rhino 5 versus Rhino 6, at the end of last class where we were using the plugin Bison to do a sort of landscape mesh manipulation on this site, I said that I would do a tutorial for those of you with Rhino 5 on this site, not using Bison, and unfortunately, I just didn't have time to do so, and it looks like I probably won't, just due to the constraints of my other job in life. So what I'll ask those of you with Rhino 5 to do is just to email me if you can't get Bison to work, and we'll just figure out something else to do. So I won't be able to do a tutorial, but I'll think of something else that you guys can do instead of doing the landscape. Finally, the last little bit of bookkeeping I want to do is just talk about where we are in the course and where we're going in the course. So ultimately, what we are going to do is we've gone up to this point where we can make essentially this abstracted Hugh Ferris style, I'll call it shadowing envelope, which also has the proper site coverage. So you've already learned a few kind of cool optimizing tricks. It also only goes up to a certain height. But from here, we're going to start working into here, and we're going to start developing some ways to look at notions of FSR, so floor space ratio. So how much area is in this building versus how much area is allotted in the lot. And then we're going to look at how to optimize that FSR in a certain manner. So today's class, we're going to also look at solar arrays as like a driver of optimization, but it's just sort of one example of what we can do with optimization. So what we are going to do in this class is we are going to essentially take this massing envelope here, We're going to break it up into discrete chunks. So, you can refer to them as voxels, I guess. So 3-dimensional voxels. And with those discrete chunks, we will then optimize which chunks we keep and which chunks we get rid of. So if I turn off my massing envelope here, we're essentially going to take this massing envelope and we're going to convert it to something like this. So yours maybe doesn't have to be so fragmented looking. There's going to be lots of ways to work within this system, but this is just a way that we're maximizing sunlight in this case, but I'm also ending up with an FSR of 9.5. So I'm going to show you how to sort of optimize within a range of FSRs using this voxel type method. The other reason why we're going to use this voxel type method, and this ties into Unreal Engine, it ties into, if you think back to the syllabus, this kind of, oh, it was in my first presentation, just let me open that. If you think about the first class presentation, I was showing all these examples where we have these kind of repeated units that sort of aggregate in interesting ways. And as I was mentioning in the first class, it doesn't have to be this like highly modernist, modular system like the Moshe Safdie here. It could be something a little bit more subtle, like this Ricardo Bofill building, or something even quite extravagant and maybe quite traditional, like this, I believe it's Chic Temple, and even crazy like this Mark Foster Gage thing. It can also be more subdued like Zaha, of course, or Sejima as well. So that's what we're doing. So we're getting to this point. So what we're going to do next class is we're going to take these voxels here and we're going to work together, and I'm going to break you up into groups, and we're going to look at these voxels and we're going to say, okay, for instance, this is a voxel that has a condition where it's exposed on all sides, it's exposed on the base, it's exposed on the top. So how can we transfer geometry into this voxel? So what I've done here is I've done some little examples of geometry. So these are those modular voxel systems I was talking about. So essentially, how do you take something like this and put it everywhere you find a condition like this? And then furthermore, how do you rotate it for different sides and everything? So that's what we're going to be covering next class. Now, the reason why I bring this up is because if we go through the schedule, you can see that, so we're sort of on schedule for this class. We're doing the programming and FSR optimization using a subtractive method. That's what we're doing this class. But the monolith class, I'm going to push to the end of all these formal intersection classes. And the reason why I'm going to do that is I'm just realizing as I sort of revisit the material in preparation for the week that it might take longer than I expected originally. And this monolith is sort of it's an add-on. It's not absolutely essential to learn for the total trajectory of the course. So I'm going to treat it as something we'll leave till, I guess it'll be the July 20th. If we get to it, we get to it. If we don't, we don't. It's fine. So essentially, we're just going to jump from massing 03 to formal intersections 02. So I'll update the syllabus to reflect that. With that being said, we'll get started. So one final thing, this is sort of ends, this class will be the last class covering assignment 2 topics. So at the end of this class, this is the work you're supposed to incorporate into assignment 2. So does anyone have any questions? Okay. Well, if no one has any questions, I'm going to get started. So like I said, I opened the assignment site in the Dropbox, and I did that so I can have access to my massing model like so. Now, I have this massing model on the layer TG massing final product. And one thing I will say, if you are using your own massing model, what's going to happen is you probably don't have any faces on the bottom of your mesh. So your mesh is open. And in order to sort of break this into voxels, we need to make sure this is a closed mesh. So what I'm going to do for those of you following along with your own site model is I'm just going to delete the faces on the bottom of this mesh. So I'm just doing this. So I'm just using delete mesh faces here. You don't have to do this. So now I'm just making my mesh open. So very simply, what you can do is you can select your mesh like so, and then you can go to mesh repair tools, and then you can just go to fill all holes. And you can see that the mesh fill all holes command is quite robust, so it works quite well. So you can see now it's a closed mesh. So you want to make sure that your mesh says closed mesh. So when you select it here and you go to properties, you'll see closed mesh right there. So just start this class with your closed mesh, and then following that, I'm going to unhide all of the site just because, enter, and then I'm going to open Grasshopper. So we're going to start with a blank file. I'm going to open my notes, of course, but you can just open a blank file. If you haven't downloaded Octopus just yet, that's fine. You can do so during the break because we won't get to it till the second half of the class. All right. Okay. So far this course has been mostly, I'd say, a multimedia digital design course. We have been using Grasshopper, but we've been using Grasshopper in a very flexible manner in conjunction with kind of GIS manipulation and just good old-fashioned modeling in Rhino. But I would say that, you know, from this point for the next 4 classes, we're going to be kind of in, well, the next 3 of 4 classes, we're going to be back in kind of pretty solid Grasshopper territory. So the first thing we're going to do here, I'll just sort of show you the first step, is we want to make a bounding box that's oriented to our mesh as best as we can. So you might have a kind of non-standard shape. So you can see I do here. It's this kind of zigzaggy thing. Bounding box by definition, Rhino has to be a rectangular prism, i.e. it needs to have 90-degree corners. So this rectangular prism, this bounding box, is not going to fit perfectly around this shape. But what we're going to do is we're going to determine kind of the major axes of this shape. So, you know, it's local north, it's local south, local east and west. So projects, you know, sometimes will have their own local coordinate system. So that's what we're going to do here. So the first thing we're going to do is, of course, we're going to reference our mesh. So having selected my mesh that we've developed last week, I'll go to Parameters, Geometry, Mesh. I'll right-click the parameter mesh, and I'll go Set One Mesh. And what I can do if I want is I can right-click this parameter, and I can rename it to something like, you know, solar massing, like so. Great. Now, if we just try to do a bounding box, so bounding boxes you do quite a bit in Grasshopper, so again, it's just the geometry that surrounds this geometry. You're going to find it's not oriented in the right way. But let's start by making a bounding box and see what I mean. So let's go to Surface, let's go to Primitive, and let's go to Bounding Box. And I'm going to take my solar massing and I'm going to plug into Content. Now the other thing I'm going to do, I have just one mass, so my, your building perhaps could be a complex of buildings, so it could have 3 towers, for instance, instead of just this one form. So what I'm going to do is on bounding box, I'm going to right click it and I'm going to set it to union box. And essentially what this does is if I had more than one object in my mesh, this would essentially create one bounding box for all of them rather than one bounding box for each object individually. Okay, so we can see that this bounding box is askew though. If we look at the top view, you can see it's oriented to the world X and world Y. And if we hover over the plane input, you can see by default it's oriented to world XY. So it's just, no big surprise there. So what we are going to do is we are going to essentially create our own plane that this bounding box is oriented on. So to do that, what we're going to do is we're going to determine kind of a main guiding edge. So we're going to say, okay, let's define an x-axis, or let's define an x-axis that kind of defines our plane. So what I mean by that is let's go to parameters, geometry, and let's go to curve. And then what I'm going to do is I'm going to right click this curve parameter. I'm going to right click it and I'm going to go to set one curve. And what I'm going to do is I'm going to select something that I think, would best define the direction of this bounding box. So what I mean is if we want our bounding box to, let's say, be aligned with the edge of this sidewalk, that seems like a pretty good way to go. We could select this. Or maybe the edge of the sidewalk here, we'd select that. So if you're doing a different site, maybe your bounding box edge is here, or it's here, but probably your bounding box wants to be aligned with your site. So I'm going to select maybe a surface edge there, choosing grasshopper, see what I get, and you can see I just get one edge right there. So this is going to be my defining edge. I'm going to just try that again. Now you can see that the reason why I chose again is sometimes you might get something that's like this, where you want to select something and it's sort of this big compound curve. So I'm going to maybe select this one. And the reason why I'm making things harder for us is just because I want to show a case where, maybe you have to break up a curve first. I just want to show something that's a little bit more flexible. So essentially I've selected the outline. In reality, you could just see if you could select one curve like that. But I've selected this outline, so I can right click this curve parameter and I can call it block outline. Jeremy, did you group the mesh when baking it? I don't believe so. I just have a single mesh right here. So I hope that answers the question. So the block outline, essentially we have one closed curve. What we're going to do now is we're going to explode this curve, and then we're just going to choose a line within it. So easily what we can do is we can go to curve, we can go to analysis. Actually, we'll go to curve, utilities, explode. So that's curve, utilities, explode. We can take our block outline, plug into the curve, and now you can see we get a bunch of segments, a bunch of vertices. So you can see there's all the segments with the vertice ends. Now, what I'm going to do is I'm just going to preview off the block outline and the curve segments. And I'm going to grab a list item because we only want to grab one of those curve segments, right? So what I'm going to do is I'm just going to go to set list item. So that's set list item. I'm going to take my segments output, plug into my list input. And now you can see if I select list item, it's just selecting this curve here. So maybe that's a good curve to choose. But what I'm going to do to make it a little bit more flexible is I'm just going to take a number slider and plug into index. So what I'm going to do is I'm going to double click on my canvas. So just double click on your canvas and that'll bring up the search function. And what we're going to do is we're just going to make a number slider, and I don't know how many curve segments you have in your block, so you can just choose a max number in your slider that's higher than the amount of sides you have. So for example, I know I don't have 100 sides in here, so I can just go 0 less than 100, like so, and hit enter. And now I just have a number slider that goes between 0 and 100. I'll right click this slider where it says number slider, and I'll just rename it to be, let's call it block edge. Block edge. And then I'll take this number slider and plug it into the index. And now you see when I select index to get a preview of the geometry and I move this slider around, you can see there's this curve kind of zipping around, like kind of reminds me of that old school game Snake, I think that's what it's called. But anyways, so that's how you just easily slide around an edge. Now, the reason why it works, even though we're sliding to the number 100 and we only have 50 segments, is because wrap is set to true. And again, what wrap does is, let's say you have a list made up of 1, 2, 3, and then you say select number 4. If wrap is equal to false, Grasshopper will go 0, 1, 2, 3, 4, and then it'll give you an error, right? It'll say there is no 4 there. However, if wrap is true, it'll go 0, 1, 2, 3, and then it'll wrap around to the end to go 4, and then it'll return the first value 0. So that's why the index can be higher than the amount of segments we have going into the list when wrap is true. So with that being said, we now have our block edge. I'm going to define the local x-axis. How you define it is up to you. It's kind of tough because Ananav is on a almost 45-degree angle from true north, south, east, west, just like downtown Vancouver, which is always super frustrating to work with. But you can't change a fictional island. So I'm going to say for me, my local north side is kind of north, I guess it would be west. So kind of this diagonal here. And if you guys want to follow along, you can do so. So just select an edge kind of on the north west side. You can select any edge you want, but it just might mean that you'll be changing some of your steps later on. But that'll become more apparent when we get to it. So for right now, just choose an edge on sort of the northwest side. So we have this edge on the northwest side. I'm going to say this is going to be my local x-axis for my bounding box. So what I'm going to do then is, since this edge is a three-dimensional object, not only does it have plan data, it also has data and elevation. So this point might be lower than this point. I'm going to project it to the world XY plane to flatten it out. So I'll go transform, affine, project. And then I'm going to take my list item, so my block edge, plug it into the geometry input, and now you can see what it does is it just projects below the site surface right there. At this point, what I'm going to do is I'm just going to hide everything. So I just hit Control A to select everything, and then I held Control and clicked my mesh to deselect my mesh. And then I'm going to hit Control H to hide everything, just so we can kind of see it. So I have my linear curve right here. Now what I'm going to do is I'm going to make my y-axis essentially. So what I can do is I can go to curve. I can go to endpoints. I'll take my projected geometry and plug it into endpoints. So now I have a start point and end point. We can see them right here. And I'm going to rotate this geometry 90 degrees from its start point or its end point, doesn't really matter which one. And then this is going to define our x-plane. So let's go to transform, Euclidean, rotate. So rotate an object in a plane. So transform, Euclidean, rotate. The geometry we're going to rotate is our projected curve. So let's plug it into geometry. The angle, we can right click on angle to set it to degrees. So I always work in degrees. So I right click, angle, click degrees. So you see this little degree icon, and then right click it again, go to set number. So right click, set number, go to 90. And then the plane is going to be the start point. So let's plug that in. Now, I was, in my kind of mind's eye, was imagining the endpoint would be the y-axis, so we can do that instead. So like that. And essentially, the reason why I'm saying that is if we think about, okay, we're building a new plane with this being our y-axis, this being our x-axis. If we look at the world y-axis and the world x-axis, this seems a little bit closer than that, Like this is a full 180 degree rotation, whereas this feels like a, less significant rotation. Maybe it's like 20 degrees counterclockwise. So that's what I'm doing here. I'm just making the axes of a new plane. So now what I can do is I can go to vector, plane, and then I can go to construct plane. So that was vector, plane, construct plane. The origin is going to be the point, your rotation point. So let's take this endpoint, plug it into origin. So now you can see we have a little mini plane there. The x-axis is going to be this one right there. So that's our original projected geometry. And our y-axis is going to be our rotated curve right there. So now you can see we have this geometry right like that. So now what happens is we have our bounding box up here, and when we plug our construct plane into it, you can see that our bounding box now aligns with our block. So what I'm going to do after this is everything here, I'm just going to group all of this. So I'm going to group. I'm going to right click the group, and I'm just going to call it setting base plane for mass bounding box. And then I'm going to group all of this, and I'll just call it mass bounding box. Okay. And you can see if we want to sort of maybe change our bounding box, we can now just go around like so. So, I mean, the reason why you might do this is, again, I'm going to preview off everything but the bounding box, or sorry, except the construction plane in the bounding box, is essentially you want to align your plane kind of like this. So you want your green line, aka your y-axis, slightly pointing upwards, and your red line, aka your x-axis, slightly pointing to the right of my screen. So essentially that's why I'm, rotating around. So you can kind of rotate it around until you get something that seems to work for you. Does anyone have any questions about that? Okay, so if there's no questions about that, essentially what we're going to do now is we're going to start making the grid around this thing. So what I mean by that, is I have a different bounding box here. That's why it's kind of weird. But essentially, let me realign this. Sure, that's better. So essentially what we're going to do is we're going to make some rectangles, so in 2 dimensions, that fit around the grid, and then we're going to move them up, and these rectangles will essentially count as units of area to calculate our FSR, but they'll also define the location of our floor slabs. So that's what we'll be doing in this next step. Let's preview off that. Okay. So, what we are going to do is we are going to essentially decompose this bounding box here. So, is that what we're going to do? Yes. So we're going to go to deconstruct box. So we're going to go to surface analysis, and then we're going to go to deconstruct box. So that's surface analysis deconstruct box, and then our box is our bounding box out is going to go into our deconstruct box in. And what this is going to give us is it's going to give us our box base plane. So you can see we have our base plane right here. That was the thing we had right there. It's also going to give us our X dimensions of the box and our Y dimensions of the box. And we're going to use this to essentially create a grid of rectangles. But what we are going to do essentially to create those grid of rectangles is we want to have squares for our units. And the reason why we want to have squares for our units is, well, I guess we'll sort of come across it later, but essentially when we're, plugging in kind of all this interesting geometry into our shape, so for example, these kind of slanted roofs, all these kind of ornate objects, etc., a square allows you to essentially rotate these kind of geometries around without having to also scale them. So it sort of simplifies the geometry. Now, in future steps, you can always create rectangular voxels in your squares, but we'll get to that later. So the important thing to remember right now is, at least in the X and the Y axis, we want to essentially create squares. So what we're going to do is we're going to essentially create a a defined dimension for our square. So let's just double click on the canvas, and we're going to set our minimum square size. So you can think about this as almost like a unit size. So maybe you want micro lofts per se, so we can say our minimum unit size is like 4, because remember we're working in meters, and I'm just going to stay in meters. Maybe I'll add a few floating point values in here, so I'll say 4.00 less than, at our biggest, maybe I'll go 50.00. Hit enter, and now we have a number slider that moves between 4 and 50. And we can right click on this number slider and call it, let's just call it voxel width and depth, aka the size of the square grids that are going across all of here. Now, what we are going to do, and I actually, sorry, I just want to, the reason why I'm kind of stuttering here is because I revised as part of the notes I remember at the beginning of the weekend. Oh, okay. Got it. Yes, I just wanted to make sure I wasn't leading us down a wild goose chase. So essentially what we're going to do is we're going to start creating some grid cells. So for our domains here, you can see essentially what's going to happen is we have a domain, right? So the x dimension of this box, which looks like it's this dimension right here. Maybe I'll sort of slide this around. So my x dimension is now this short dimension. You can see that my x dimension goes from negative 16 to 79. So it's sort of negative 16 to 79. And what we're saying is we're saying divide this width by approximately a width of, in this case, I'm going to set it to be 15 meters. So what we can do is, first of all, we need to figure out negative 16 to 79, what's the actual length of this edge. So to convert a domain, an x dimension of the box, to an actual length, we can simply go to parameters, primitive, and then number. Take our x dimension and plug into number. And you see what this is going to do is it's going to automatically go 79 minus negative 16 equals 95.98. So we can right click on that number and we can just call this x dimension. And we'll do the same for y. So what we can do is, again, we can just go parameter, primitive, number, take the y dimension of the box, plug into number. It gives us the overall, I guess, depth. So in this case, you can see a domain 34 to 188. So 34 to 188 equals 154. So I right click that number and call it y dimension. And now what we're going to do is we're going to divide these dimensions by this voxel width and depth. So let's go math, operators, division, right there. Now our x dimension, we're going to divide it. So x dimension goes into A, and we're going to divide it by our voxel width and depth. So it'll tell us how many cells we can fit within this width right there. So the result of our x dimension divided by the voxel width and depth equals 6.39. So we're not going to work with fractions of cells. So we can say we can fit 6 cells along this direction, and there'll be a little gap there, but so be it. And then so we're going to do the same with the y dimension. So how many of these 15 by 15 cells can we fit along the y direction? So let's go to math, operators, and division. We're going to take our y dimension, plug into A, and divide it by our voxel width and depth. So that plugs into B. The result is 10, so we can, or 10.2, so we can fit 10 full grids in this long direction. So since we can't fit fractions of grid cells, what we're going to do is we're going to round down to the nearest full grid cell. So to do that, simply what we can do is we can go to math, utilities, round. So that's, I'll grab 2 of those, math, utilities, round. Of course, you can always just go Control-C, Control-V to copy it. We'll plug our result into the round component. So that's the result from the x dimension, the result from our y dimension into the round component. And we're going to be interested in the floors of both. So that's the first integer smaller than or equal to x. So that's what we're looking for. So now we know that we have a grid from 6 in the x direction by 10 in the y direction. So maybe let's just group that now. And then we'll call this assigning grid dimensions and amounts. So we're figuring out, the grid cell size, and then we're figuring out how many of those grid cells we can fit within our bounding box. But now what we need to do is we actually have to draw the rectangles. So we're going to do that by dividing the domain of this bounding box. So what we can do is we can take the first value in the X domain, the first value in the Y domain, and then kind of keep on adding the width and depth of our voxels to it to sort of create this new set of subdomains. So what I mean is, let's go to sets, or let's go to math, domain, deconstruct domain. So math, domain, deconstruct domain. I'm going to need two of these, so one for X, one for Y. So again, that's math, domain, deconstruct domain. The X domain, I'm going to plug into the first deconstruct domain. The Y domain, I'm going to plug into the second deconstruct domain. Maybe I'll put the X one above our X round, the Y one below our Y round, just so it's kind of organized. And essentially what I'm going to do is I'm just going to make a series of values. So I'm going to go to set, list, or set, sequence, series. Going to need two of those, so let's go set, sequence, series. And what we're going to do is we're going to start at the start of the domain. So the start of X is -16. Yours might be different. So the start, I'm going to plug into the start. The step size for each successive number is going to be our voxel width and depth. So we're increasing the steps by 15. And the count is going to be the floor. And now you can see what we get is -16, -1, 13, 28, 43, 58. And if we look at our domain end here coming out X, our end is 79. So you can see that we can fit in one more essentially value of 15. So what that means is essentially if we're talking about steps, and I've talked about this before, remember if we're talking about steps, steps are the kind of spaces, actually, sorry, that's not a good drawing. Let's say we have three values, 0, 1, 2, that's three values, we have two steps between them. So sometimes when you want to essentially get one more step, you have to add one more value. So what we can do in this case is we can go to count, so number of values in the series. We can right click it, we can go to expression, and we can go X plus 1. So now you can see our max is 73, which is still lower than our end of 79. We're going to do the same thing for the Y value. So our start is going to be the start of our deconstruct domain. Our step is going to be our voxel width and depth. So plug that in. And the count is going to be our floor. So let's plug it in there. So series equals 34, 49, 64, 79, all the way up to 169. The end of our Y domain is 188. Again, 169 plus 15 is it's, I guess, just barely below that. So essentially we can do the same thing. We can right click, expression. So I right clicked on count. I went to expression and I typed X plus 1. And now our final value is 184. That's still smaller than 188. So from there, what we can do is we can create new domains. So right now we created a series, but what we're going to do is we're going to take these series and create a domain based on these plane. So to do that, we can go to math, domain, and then consecutive domains. So create consecutive domains from a list of numbers. And simply what this is going to do is if we have a series here that goes -16, -1, 13, 28, etc., etc., it's going to say, it's going to create a list of domains that goes -16 to -1, -1 to negative 13, negative 13 to 28, and so on and so forth. And that's what we need to make rectangles. So that's why we use this component consecutive domains. So we can take our series output from our deconstruct domain. So the x values plug into numbers. And now you're going to see we're not going to get what we want at first. So negative 16 to negative 18, negative 18 to negative 5. And that's because our additive, I guess, option is set to true. So we don't want to add up these values when we're making domains. We just want to make domains. So what we can do is we can right-click additive, go to set Boolean, go to false. And now you can see that our domains are negative 16 to negative 1, negative 1 to 13, 13 to 28, 28 to 43, and that corresponds to the negative 16, 1, 13, 28, so on and so forth. So that's how we create domains from a series of numbers. We can just do the same thing for our y values. So let's go to math, domain, consecutive domains again. Plug our series output into the numbers input. And let's just switch our additive. Let's right-click additive, go to set Boolean, false. So make sure it's false. And now our domains are 34 to 49, 49 to 64, and so on. And that corresponds to 34, 49, 64. So you can see that our series has been properly converted into domains. So let's group this. And I'll right-click this group. And I will call it constructing subdomains. So before I ask the usual any questions, I'm going to show you what all this means in Rhino. So we have all these domains now. Now we're going to construct rectangles from them, or rather squares. Thanks, Roy. And let's go to, oh man, okay, sorry about that. Let's go to rectangle. So let's go to curve, primitive, and then rectangle. So that's curve, primitive, rectangle. And essentially what we're going to do is we're going to draw a bunch of rectangles. So this component creates a rectangle on the plane. The plane is going to be our plane we've created, right? So it's going to be our bounding box plane. We don't want to create it on the world XY plane, or else it's going to draw our rectangles over near the origin and they won't be aligned with our bounding box. So we can simply just grab our plane from our deconstruct box. So our deconstruct box, the plane output, let's plug into the plane input. So that's plane output of deconstruct box, plug into the plane input. Zoom in so you can see it. The x size is going to be our x domain, so that's the top domain. So again, we have our deconstruct box x values going into the deconstruct domain, going into the series, going into consecutive domains. So let's take the top consecutive domains, plug into x size. So now you can see what's happening is it's drawing grids that roughly align with the x value of our bounding box. And then the bottom consecutive domains, let's plug it into the y size. Now, when I first plug in, it's not going to give us exactly what we want, because you can see what's happening. It's that whole data management thing. So what's happening here is that Grasshopper, you can see that if we hover over, let's just grab a panel. You don't have to do this. I'm just explaining something here. So we can go to params, input panel. So what you can see is that there is one list in our X domains. And then I'll grab another panel, show you the Y domains. So there's one list in X, which is right here, and this list has an address, or rather a path, of 0, 0, 0, 0. And it has 5 items in it. So these, or it has 6 items in it. So they're all domains. Our Y domain, since our Y side is longer than our X domain, it has 10 items in one list. This list has the address or the path of 0, 0, 0, 0 as well. You can see that what Grasshopper is doing is it's matching the first X domain with the first Y domain, the second X domain with the second Y domain, third X to third Y, all the way till it gets to what would be the index 6 or the 7th item in Y. And at that point, it's ran out of X domain, so it just keeps repeating the last X domain. So that's why you get this kind of fall off effect like that. So what we want to do is we want to match each of these X domains to all of these Y domains, and that will give us a 2-dimensional grid of rectangles or squares. So what we can do is we can right click our X size and click graft. So right click the X size input and go graft. And now you can see what's happening is for each of these, here, I'm just gonna graft it right here as well so we can see. So now what's happening is each of these X domains are in their own list. And so what's happening is it's matching list to list. So it's gonna say, okay, we have one domain here, match this one domain. So that's right here. Match it to these 10 domains. So that's why you get a column. Match this domain, so that's right there. Match it to all the Y domains. So that's why you get these columns, and that's why you get the 2-dimensional grid. So that's how we make sort of our 2D rectangles. So what I'm going to do now is I'm going to select all of these components. I'm going to right-click outside them. I'm going to go group. I'll right-click this group, and I'll call this constructing the initial 2D grid. Now, the interesting thing about this is if we, let's say, look at this thing in plan, I'm going to hide my mesh as well. You can see what happens is that it isn't exact, right? But this is fine because you can see that certain values fit better because we can't have fragments of grids. So you could go through, and if you want to get a super high resolution grid, you could, decrease your voxel width and depth 4. Or probably what I'd do is find a larger number which fits pretty well. So for instance, I might go 18.99. I'd round it up to 19. It still fits quite well. I'd say perfect. 19 is my unit. Yeah, Erica. What if your grid ends up beside and not underneath your bounding box? If your grid ends up beside and not, let's see if I can make mine do that. So you might want to try choosing a different side. You can see I'm choosing going around, and I can get something that's not quite aligned if I choose one of the kind of corners of my site, but that's probably not your question. It has something to do with your value. So maybe what I'll do is, so everyone can be at this same point with the geometry I'm using, is I'll save this file in Dropbox where I am right now. So I'll save this in Dropbox, Erica, and then after class I can take a look at yours because it'll be kind of hard to answer without seeing what you're working on. Okay, so under lecture files, under today's date. So while I'm saving this, are there any other questions about this? Oh. Okay. So for everyone who either maybe fell behind a bit or who had an issue, you can use the Grasshopper file I just saved in Dropbox. and you can use the mesh that I have in the file, and you'll be able to follow along. And if you do have an issue, I can just address it during the break. Actually, it's probably a better time. Yeah, it could be that. So Nicholas is saying that there could be an issue with the C-plane in Rhino, but again, we'll have to look at it. Okay, so from there, we have this one rectangle. And essentially what we want to do, so I'm just going to go and look at my notes here, is we are essentially going to keep on repeating these rectangles until they kind of reach the top. So we're going to take this 2D grid of rectangles, and then we're just going to move them up. From there, we're going to extrude three-dimensional bounding boxes from them, and those will define our voxels. Now, so I'll preview off that. So, Okay, I understand what I'm doing again. Again, I prepped this class in advance, so sometimes with Grasshopper stuff, that's why it's good to write notes to yourself so you can quickly look at your work and kind of remember what you were getting at. So what we are going to do is we are going to do something similar to what we did for the X dimension and the Y dimension. So essentially what we are going to do is we are going to start out by figuring out how tall our building is. So to do that, we can convert our Z domain to a single height value by just plugging it into a number parameter. So let's go to parameters, primitive, and then number. Take our Z output, plug into the number input. So you can see what it does is 11.97 to 250. It just subtracts the end of the beginning of the domain from the end of the domain, giving us a value of 238. So we can say that the height of this bounding box is 238 meters tall. So let's right-click this parameter and call it Z dimension, or you could just call it height if you're not a nerd. So Z dimension or height. From there, what we're going to do is we're going to define our floor heights. So when you're working on a tower, usually what's going to happen, and you could go about and sort of nitpick the height of every single floor, but usually what's going to happen is you're going to have retail or some sort of amenity on the first, 4 or 5 floors. Maybe sometimes it's only the first floor. And those are going to have a certain ceiling height, and then you probably are going to have a repeated slab height, like floor-to-floor height for the majority of the rest of the tower. Sometimes you might have something fancy in the middle. But what we're going to assume for these towers is that we have a repeating kind of last height. So we say, okay, we have 5 or 6 special floors, they're amenities. And then after that, we're just going to have however many floors we can fit in with a repeated height of, a certain amount. So what we'll do is we'll create a panel. So we'll go to params input panel. Now, we can right-click this panel, and we will just call this floor-to-floor height. So this isn't ceiling height, it's going to include your slab and everything. So in other words, if you want, 12-foot high ceilings, then your floor-to-floor height is going to be 13 feet. 15 feet. We're working in meters here. So since we want to define more than one floor height, I'm going to right-click the panel. I'm going to go to multi-line data. And when you right-click a panel and go multi-line data, it just converts your panel from kind of a thing that can hold one piece of data to a list that can hold multiple pieces of data in the standard Grasshopper list format. So what we're going to do is we're going to start entering some floor heights. So Let's say our first floor, so we're working from the ground up. If I look at my kind of floors here, you know, you could kind of figure out what you want. So I'm just going to say my first floor is going to be, let's say, 3 meters. So this is going to be like a basement floor. It's going to probably go in there. So meters to feet is approximately 3.3. So essentially what that means is we're going to have, you know, it's going to be 10 feet. It's going to be quite a short storage area. After that, I'll say I have like a big, very big story for the first floor. So let's say maybe I have 5 feet. So that's like, or even 6, a very grand entrance. Then maybe I have an amenity space that has 5 feet. And then after that, I'm going to have the rest of my apartments, which have maybe, so 5. And the rest of my apartments are going to have a height of 4 meters. So essentially what that's going to give you is, you know, about, I don't know, 10-foot high ceilings. So it's a nice apartment building. So we have, so I'm going to click out of that. So you could have different things. You can play around with different values, but essentially what's going to happen here is our first floor, which is my site's on a slope. So it's going to be this back portion here is going to have a very short ceiling height, then a very grand ceiling height. So that's going to be like 20 feet. And then, you know, around the 15-foot high, you know, or 12-foot high ceilings for the second amenity. And then following that, kind of quite gracious apartments the rest of the way up. So 4 meters up. So what we're going to do is we're going to figure out how many floors we can fit in there. So to do that, let's first figure out how, what the height of the first 4 floors are. So to do that, let's go to Maths, Operators, Mass Addition. Take our floor to floor height, plug it into the input. And now you're going to see our result gives 18. So our first 4 floors is 18. The height of them is 18. What we can do now is we know our Z dimension here. We can go to Math, Operators, Subtraction. We can take our Z dimension, 238, plug it into the A input. Our mass addition output, so our result output will plug into B. And what this will give us is the amount of height left after our first 4 floors. And essentially, we're going to divide that by our value 4. So essentially, the last number in this list is going to repeat over and over and over and over. So let's do that. So what we can do essentially is we can go to Sets, List, List Item. So the list we want to take an item from is our floor to floor heights. Let's plug into List. The index is going to be -1. And again, wrap is going to set to true. And again, the way this works is, let's say we have a list of 0, 1, 2 values. So let's just say our list is 0, 1, 2. If we choose index 0, it's going to give us 0. Choose index 1, it's going to give us 1. Choose index 2, it's going to give us 2. But since wrap is on, if we choose -1, instead of moving forward in the list or right in the list, it's going to go backwards. So wrap left around the list, and -1 is going to always be the last item in the list. So that's why we can right click on our index input, go to set integer, and set it to be -1. Go to commit changes. And now if we hover over our item output, it is 4. The last item. You know, if we change this and let's say we want to change it to 4.5, the last item is still 4.5, so it doesn't really matter. Okay, so now we have the last item here. We have the result, so the amount of height left over after our first now 5 floors. So what we're going to do is we are going to take this result and divide it by the height. So we'll go to Math, Operators, Divide, so division. So Math, Operators, Division. we're going to divide our remaining height by the last floor defined, or the last height defined. That gives us a value of 47.89. And in a similar manner to, defining an XY grid, we can't have, 0.89 top floor, or else, maybe it's your mechanical room or whatever. For the purposes of this assignment, we're only going to stick with whole numbers. So what we'll do again is we'll go to math, we'll go to utilities, and then we'll go to round. We'll take our division result, plug into the number input of round, and then we're going to choose the floor. So again, how many whole floors can we fit in this bounding box after our first 5 floors? And then what we're going to do is we're going to repeat this data the amount of times that comes out the floor here. So what we'll do is we'll go to sets, sequence, repeat data. The data we want to repeat is our list item, so aka the last item in this list. So let's plug into data. And the length that we want to, the final pattern to reach, how many times are we going to repeat it, is going to be the floor. So let's take the floor, plug it into length, and now we get 4.5 repeated 47 times. Now, what we can do is we can just merge these lists together. So we can take our first 5 values and then merge them with these last 47 values. In my case, 47, maybe yours is different. So let's go to sets, tree, merge. So that's sets, tree, merge. Data 1 is going to be our floor-to-floor height list. So our first however many floors, plug into data 1. And then data 2 is going to be our repeated data. So let's plug into data 2. Now, if we look at the result right here, oh, actually what I did right there is it automatically populates a third data stream. I just zoomed in and clicked the little negative to get rid of that dangling stream. So if you look at what's going on now, essentially our first set of data, so our 5 first floors, has a path of 0. So that's the address of that list. And our second input, so our data input 2, has a path of 0, 0, 0. So that means that's its address. And what that means is that we've done 3 steps on it. So if you look at this list here, the output here, let's see, the mass result here is 0. When we look at the subtraction, it's now at 0, 0. When we look at the division, it's 0, 0 still, but when we look at the floor, 0, 0. When we look at the length, or the repeat data, now it's 0, 0, 0. So essentially what's happening is at different stages within this algorithm, we're sort of adding superfluous branches to our data structure. So to get rid of superfluous branches, because this is still one list, so we don't need these extra leading zeros, we can just right-click our data output of repeat data and go to simplify. So right-click data out, go to simplify. And then now you'll see our result is, oh my goodness, so it didn't do it. And if that doesn't work, you can always right-click and go flatten for both your inputs. So yeah, D1 is our original floor-to-floor height. So you should be able to simplify output and fix that problem. I was taking that as a teaching moment. But when all else fails and you want to merge data into one list, you can always just flatten the input. So again, for both D1 and D2, I just right-clicked and going flatten. Yeah, so Natalie, the reason that's absolutely true. So Natalie is pointing out that if you only flatten D2, it'll work. And the reason why that works is, just for a bit of background info, if you look at the result here, our first list here has an index of 0. or rather a path of 0, and the default path in Grasshopper, if you just have one list of data, is 0. So when you flatten data, you're going to revert it to this default pattern. So that's why you just have to flatten D2. I mean, out of kind of a, what's the COVID term? An abundance of caution, I like to flatten all the inputs to kind of avoid any kind of mess that could occur. But anyways, regardless of how you get to work, essentially what we get out of the end of this is one list with 52 values. So that's great. So what we can do now is we can just group these. So let's group all of these components here. Let's right click the group, and we can just call it floor heights. So perfecto. Okay. Great. Now we have our floor heights. What we want to do now is we want to take our grid that we have here, and we want to move it up by these heights, and then after that we want to extrude them, right? So the first thing we'll notice though is that our rectangular grid is below our bounding box. So the first step that we need to move up our, or the first amount that we have to move up our grid by is from 0, so an elevation is 0, up to the bottom of our bounding box. And since we know our grid is on 0, what we can simply do is we have our deconstruct box right here. We can go to maths, domain, deconstruct domain. So that was maths, domain, deconstruct domain, and we're grabbing it from our deconstruct box, getting our Z value here. So it should look like something like this. And this start value, so in my case 11.97, that is going to be the first value we move this grid up by. So what we can do then is we can essentially take these our merged values, so all our floor heights, and we're going to merge it again with this deconstruct domain start. So to do that, let's go to sets, tree, merge. So similar to last time, sets, tree, merge. Take the start, plug into data 1, and then our merged results, let's plug into data 2. So now, because we don't need D3, I'll just click the little negative symbol after zooming in. And now you can see similar things happening where we get a 0 and then a 0, 0. What we can do is we can just flatten our inputs, or in this case, flattening D1 will probably just work. Yeah, so you can flatten both though, just out of habit. And you can see what's happened is we have the same list coming out of our previous merge, but then now we have this 11.97 in my case, or in your case it's going to be the sort of bottom elevation of your bounding box before all your ceiling heights. Okay, so now we have two things. We have our floor heights, and we have essentially the floor elevations, as it were. Now we need to do 2 more steps to these floor elevations to get into a kind of a working order for us. So the first thing we're going to do, Jeremy, the deconstruct domain input came from the deconstruct box. So So the deconstruct box at the beginning of our constructing the initial 2D grid. So essentially what we're going to do now is, if we think about it, out of our first merge, we have essentially our floor heights. But out of our second one, we have our the elevations. So if we look at our elevations right now, what we have is 11.97, then 3, then 6, then 5. And here, I'm just going to do something. Maybe this is a way to do this. I just want to refer to this list of numbers here. Okay, so essentially, we have 11.97. Our grid right currently is at 0. So this line down here is at 0. So 0. What we are going to do is we're going to take our grid, we're going to move it up by 11.97. So 11.97 to right there. But then now what we're going to do is we're not going to take this one in some sort of iterative looping way. We're not going to say, okay, take this one and then add 3. What we're going to do is we're just going to take this original one and then go 11.97 plus 3. So what we're going to do is we're going to move this up 14.97. And then we're going to go 14.97 plus 6. So that's 20.97, and so on and so forth. Now, after we do that, we're going to extrude those floors. So that's what we're doing. The one thing that we have to think of, though, is if we're, let's say we're moving up our floors to, maybe it's easiest to do this first and then explain after. That's what I'll do. So what we're going to do then is let's mass add up our elevations here. So we're going to go to maths operators mass addition. So maths operators mass addition. We're going to take our results here. We're going to plug into input. And then we're going to take the partial result. So now what you can see is we have that 11.97, the 14.97, 20.97, et cetera, et cetera. And if you look at this, we have 53 results. But if we look at our original result of the merge, aka our ceiling heights, we only have 52 values. And so that means that we have to delete the last value of our elevations. And the reason why I say we delete the last value of our elevations is, think about it. If our grid is at 0 to start out with, and then we move it up to 11.97, let's just round it to 12. And then after that, we move it to, let's say, we add 3 more, so we move it to 15. And then let's say finally, we have another value, which is also 3, so then we move it to 18, right? So there's our other roof. Since we have one more elevation than we have floor heights, what's going to happen is we'll be able to fill in the floor here. We'll be able to fill in the floor here. Oh, sorry, we don't fill in this one here. So we fill in the floor here, we fill in the floor here, but then we don't fill in the top floor, right? Because we just don't have a floor up here. So I think I explained that right. I sort of scribbled it wrong. But anyways, we need to match 52 floor heights with 52 moves. So essentially what we're going to do is we're going to go to sets, sequence, call index. And then our partial results will plug into the list. And then our indices is going to be -1. So right click on indices, go set integer -1, click commit changes. And then our wrap's going to be true, because remember, if wrap's true and indices is -1, then you're always going to get rid of or choose the last one. So I want to re-explain why we got rid of the last one, because I hate when things are kind of stumbled through. So these movements here represent the floors. So this is the way to explain it. So if we have our original grid here, which we're not using as a floor, it's kind of an abstract thing floating beneath our bounding box. and we're originally moving it up by 12. We get our first floor, right? So that's a floor. And then we move it up by another 3, which in total means we're moving up by 15. That gives us another floor. And then what we're going to do is we're going to move it up. We have a final value that's also 3, so that's going to move it up to 18. That is another floor. So these are, we have 3 floors. So floors. What happens is since we added a value at the beginning, we have 1 less ceiling height than we have floors. So if you think about it, what happens is we have a ceiling height, we take this floor and we extrude it by 3. So that's our first value, 3. And then we take our second floor we have in this list and we also extrude it by 3. So then that's our ceiling height there. But if you think about it, we're left with this one final floor, but since we have no more extrusion distances, we can get rid of it, and it doesn't matter because we've already extruded the room below it, as it were, to the proper height. So it's just kind of an extra floor. So that's why I'm saying we can get rid of this last item. So that's why we can do that, if you're wondering. So I hope that's a little bit clearer. So now that we have this list here, so this is our list of movements. This first list is our floor heights. What we can do is we can go to transform, Euclidean, move. So that's transform, Euclidean, move. So move needs 2 things. First, it needs the base geometry. So what we're going to do is we are going to, first of all, we'll take our rectangles. I want to make sure that this is correct. Yeah, so what we're going to do is we're going to first hook up our geometry into the move. We're going to take our rectangles that we have coming out of the end of this group here. So these are our 2D rectangles. We're going to flatten them because we want to apply the same movement vector to all rectangles. So right-click your rectangle output, click flatten, plug that into the geometry input of move. So you can see 40 rectangles in my case going in. And then what we're going to do is we have all these values, but we need to give them a direction now. So to simply give them a direction, we know our direction is going to be up. What we can do is we can go to vector, vector, unit Z, take our list output, and take this unit vector, plug into motion. And now you'll see, again, in 3 dimensions, I'm getting a similar thing that I got before with the 2D grid, where what's happening is these vectors, I have 52 vectors, I have 40 rectangles. What's happening is since I have more vectors than I have rectangles, it's matching up 1 to 1, right? Up till the point where I'm on my 41st vector, and then for the remaining vectors, it's just repeating the final rectangle. So to apply each vector to all rectangles, what I can do is I can right-click on the unit vector output and go graft. And now you can see it's applying one vector to all the, or each vector to all the rectangles. So the rectangle output is flattened and the vector output is grafted. And that gives you this 3-dimensional grid like so. Now, what we are going to do is we are going to create 3-dimensional voxels or bounding boxes out of them. So we have our ceiling height, so it's pretty easy to do now. We can go to surface, primitive, and then we'll go box rectangle. So that's surface, primitive, box rectangle, and you can see when I hover over it, it says create a box defined by a rectangle and a height. So that's perfect. Plop that down on the canvas. The rectangle will be all of these rectangles we have here. And what we can do is, just so it's a little bit clearer for us, is if we right-click our rectangle input, you can see, let's just hover over it. So you can see I have all these leading zeros on my path. So 0, 0, 0, 0, 0, 1, 0, 0, 2, 0, 0, 3, all the way to 0, 0, 51, representing the rectangles in each level. If I just right-click that and go simplify, now it's just nice and simple, right? Like all our paths are 0, 1, 2, 3, 4, 5, 6. And that's, I like simplifying just to sort of get rid of all the excess visual, I guess, garbage. So what we're going to do now is we're going to take the results of our original merge and we're going to plug it into height to extrude it. But what I'm going to do first is, if we look at our results output, we have 52 of them. You know, it's not a coincidence that we also have 52 paths containing 40 rectangles each here. But what we're going to do to match sort of one height to each level is we're going to right click on our height input, go graft, and then we're going to right click on our height input again and go simplify, just to sort of make things nice and simple. And then we are going to take our result of the merge. So this is sort of our first data merge that's coming out of our floor heights group here, and we'll plug it into the height input. And now you can see what happens if I preview off all the other stuff leading up to it. Let's preview off the bounding box and everything, and this original mesh, so we can just see a bit better. We have this kind of this stack of meshes, right? So this is what we want to see. We just have all these box rectangles. So we can group all of these. And let's right click on this group and just call this stacking the voxels. Now what's kind of cool is, like, let's say I want to increase my floor height. So I have some, you know, let's say some eccentric people living in this building who want super high ceilings. You know, we could increase their ceilings to, let's say, 10 meters. At the end, click out of this, and now all of a sudden you can see 10 meters. Another thing too is, like, coming up in the future, you might want to use bigger voxels and fit, you know, more than one floor in each voxel. But I'll let you get to that when we get to that. But for right now, just know that we've established this kind of flexible system. So Cecilia says, my base bounding box plane is in the ZX plane and I can't get in the XY plane for some reason. I will take a look at that during the break. So if you just follow around as best as you can, and then I'll take a look at that. Yeah, sorry guys, it's really harder than usual to kind of handle these live questions, I find, because so much of this depends, like, there's, you know, of course you've seen Grasshopper, even all these, there's so many little things you can, you know, make a mistake on. It's so easy. I do it all the time, and you just need to go through step by step. So the one final thing we want to do before we take a break here is we want to essentially get rid of the bounding boxes that are kind of outside of our shape. So if I'm just going to click Control-Shift-H in Rhino to turn back on my mask, and you can see that I have all these kind of boxes, like, let's say right here, which kind of fall like well outside of my massing shape here. So now we're just going to get rid of the voxels, which totally fall outside this shape. So I'll hide that again. So the first thing we want to do is, for all these box rectangles, let's go to vector. Actually, easiest way, did I do it that way? Yes, I did. Okay, nice. Let's go to surface analysis, and then let's go to box properties. So surface analysis, box properties. Box output plugs into the box input of box properties. And you can see that just easily gives us our center points of all our boxes. So that's great. Also gives us the area, volume, etc., etc. So that's kind of cool too. But what we're going to do is now we are going to go to mesh analysis, and then we're going to go to mesh inclusion. So test a point for mesh inclusion. So what that means simply is a point inside of a closed mesh. And that's why we made sure our mesh was closed at the very beginning of this lecture. So mesh analysis, mesh inclusion. The mesh will be way back at the beginning of your definition. I'm going to move this down a little bit. So way back at the beginning of your definition, you have your solar massing mass. Essentially your mass, right? Like it's this shape here. So take this mass, bring it all the way to the front to this mesh inclusion component, plug into mesh. The points will be center, and we'll plug that in. And it might take a second to kind of figure things out. And essentially what we're going to get is a bunch of trues and falses out of here. So let's just go params, panel, and I'll just look to show you. So we have a bunch of falses. It means it's outside of the mesh. And then we have trues when it's inside the mesh. So simply what we can do now is we can go to sets, sequence, call pattern. So that was sets, sequence, call pattern. And our list will be our box rectangles. So take your box rectangles, the box output, plug into list, and the call pattern will be the mesh inclusion inside output. So we can preview off all this stuff preceding that call pattern. And now you can see if I turn off my mass, I have this kind of voxelized, 8-bit version of my mass. So this, you can make this more of a higher resolution if you so wish. The smaller your voxel is going to be, the closer it's going to get to your original mass. But as you can see right now, and I really hope the stream isn't freezing, that if you do go small in your voxel width and depth, it does take a lot of computational power. So yeah, you can see there the shape gets a little bit better. So I mean, personally, I wouldn't go for something this dense. Please keep in mind that you'll be adding detail into this later. So I would, aim for a voxel width and depth. Maybe I had mine at 19, so I would aim for somewhere around 20 meters. I'd say 10 at sort of the minimum, because we will be compiling all of these together in one giant file at the end of class. So does anyone have any questions about that before we take a, let's say, a 10-minute break? Okay, so if that's the case, we're going to take a break till 7:43, and I'm going to say 10 minutes because I'm going to take a look at, I guess, Erica's problem, unless it was solved. So Erica, let me know, and Cecilia's problem. So if you could just email me your grasshopper. Okay, so yeah, so. How about Erica, could you email me your grasshopper file? And also, are you working with the mass that I'm using in the class demonstration? So it looks like Colin's having the same issue, so it'll probably be instructive to sort of look at this as a group. Okay, there's a lot of weird things going on. Okay, so for essentially what I'll do is Erica, Colin, Matt, send me your Rhino file and the Grasshopper file. Cecilia, also send me your Rhino file and Grasshopper file via email, and I'll sort of just address the files as I get them. Okay, well, while you guys send that over my way, I'm just gonna go grab a glass of water. So I'll just be back in a minute, and then we can quickly dive into it. So again, please send me your Rhino files and Grasshopper files. Oh, hi all. Sorry, so my mic was off, but now I've opened Colin's file, and I'm hoping that this is illustrative of, the issue that a lot of you are having. So, I guess, Colin, is this kind of similar to what yours is doing, and also Matt and Erica? Or this is kind of similar? Yes. Okay, great. Perfect. So let's go and see what happens. So essentially what I think is happening here is probably something with the domains. Oh. So the way I kind of like trying to check this is just why don't we just look at the X size first? So I'm going to disconnect this. I'm going to look at the X size. So it's the X size that's going the wrong way. So, I mean, if this is happening, what that tells me is that your X plane is probably just in the wrong direction. Okay. So what I did there is I just set it so your X goes in the negative direction. But I think ultimately what's causing this is if we go way back to the beginning of our construct the plane, what you can do here is if you are getting this, I think it's just ultimately that your line that you chose, for some reason, it's just behaving differently than the way my line behaved. So what you can do is in this angle, I believe if you, instead of going to set number equal 90, if you just set it to set number equals negative 90, oh, that's not what we want. Maybe let's leave that 90. Instead, why don't we try using the start of our line for our origin, and then the start of our line for our plane, and that will work. So, okay, so if we go back, essentially what's happening is we have our northeast alignment curve, right? And essentially what it means is just this curve was in a different direction than mine. So whereas I based my construct plane based on the endpoint, so essentially I had my projected curve, and then I chose a curve, and then I went and used my endpoint to define the beginning of the origin for my plane, and then I chose my endpoint to rotate my x-axis. For you guys, you might just want to use your start point instead. So what I did is I took my endpoints and I plugged the start into origin and the start into my plane. So, Erica, did that fix it for you? Okay. So the other thing you can have, if you do have that issue, that worked, except it needs to be on the other side of the curve. Okay, so it's so the other thing you can do is, let's say you want to also keep your your plane the same way it was. So right there, another thing you can always do is you can go to your steps and you can just right click on your step. So essentially I'm in my initial 2D grid or 2D grid group, And on my constructing subdomains, if I right click on step and just go expression and click or type -x, that's also just going to flip the domain of my grid. So there's a bunch of ways of sorting or of fixing this issue. So you can see that kind of then works for me. So there might not be one fix necessarily for everything, but I think that should give us something kind of close. I'll have to that could be another solution. So if that doesn't work, Erica or anyone else who had that kind of issue, just let me know at the end of class. I kind of want to move on, so we can tackle that at the end of class. I will, however, look at let's see. So I will look at Cecilia's because she has a different issue, also related to the sort of, I guess, planes. So I will take a look at that one if it's going to download right away. Let's see. Okay. So for people who are just coming back, essentially I'm looking at a file where the grid is going the wrong way. So maybe some of you might have that issue as well. Okay. So what we have going on here, oh, wow. Okay, so in this case, the grid is in the wrong place. So you know what? I'm going to go through this after class, Cecilia. So for anyone who has questions, I can't address them after class because otherwise we won't cover everything. So if you are having an issue, what I'm going to do is I will save what I've done up to this point in the Dropbox right now. So you can go File, Save Document As, and I'll just save in the Dropbox. So under today's class file, Voxels Part 1, I'll just go Program Voxels, and then I'll just append a little 1 or maybe 2 at the end of it. Okay, just because I want to keep on moving forward. Okay. All right. So now we're going to do something that's kind of interesting. So essentially what we're going to do is, and we probably, now that I'm looking at the time again, we probably won't get to the end of this today, but that's okay. We'll sort of get to the start of it, and then we'll finish up next class. So essentially what we're going to do, if I'll just preview this off, we're going to use the plugin Octopus. And what Octopus is going to allow us to do is going to allow us to take our called pattern, like the one I just had, right? And like the one that you guys are working towards. And we are, oops, what did I do there? And what we are going to do is we are going to use an optimizer like Galapagos to essentially calculate a trade-off between FSR and solar exposure. So we're going to say, okay, if I look at the FSR of the voxelized mass as it stands right now, it's going to give me something like 17, right? So this has an FSR of 17. Our max FSR for assignment 2 is 10. Our min FSR is 6. So the question is, how can we get rid of blocks from this mass that brings us back into this FSR range of between 10 and 6, but at the same time, how do we do so in a way that solves or optimizes for something else? In our case, we're going to solve for solar exposure. So what units, what blocks can we take out of this mass to reach our target of between 10 and 6, but also increase the amount of sunlight that as many units as possible receive? Octopus, just to show you quickly what we'll end up with, will give us this really interesting way of doing that, where essentially it is going to... So I'm showing you the octopus screen. We'll get to this. Essentially what it's going to do is it's going to give us a trade-off. So it's going to say, okay, if you go, FSR 8.3, you can really reduce the amount of shade your building casts on itself. But if you go FSR, let's say 9.2, you're going to have more shade. So I let this optimizer run for 2 seconds, so it's not giving us very good results. But if you let this run for quite a bit longer in a similar way to Galapagos, but in 2 dimensions, we can sort of choose a bunch of design solutions. So it's going to be really interesting. So this will allow us to sort of iterate through different iterations of this. And that's why if you look at, if you're using the class file, my TG FSR Voxels 9.5 FSR layer, that's how I ended up with this thing like this. So what I did was I took the same pile of voxels that we've built up to this point that's roughly in the shape of my solar massing, and then using Octopus, I balanced solar exposure with the FSR range to sort of chip away at the mass to get this kind of interesting, very activated space. So that's where we're heading with this. So let's get going. So what we have right now is we have our pile of voxels. They're roughly in the shape of our solar massing. So, for assignment 2, I said don't shade the street across the road. If your voxels poke out of your solar envelope, for the sake of this course, don't worry about it, right? As long as you're building your pile of voxels based on this methodology, you're close enough. So we have this call pattern coming out. I'm just going to group it right now. So we have our pile of voxels here. The next thing we need to do is figure out the current FSR so we can compare it to our desired FSR. So what we're going to do is simply we are going to, first of all, we're going to flatten our list of, we can flatten our list of boxes. We don't really need the floor information anymore. So 1264, that's how many boxes I have in this list. And then what I'm going to do is I am going to go to surface analysis, and then I'm going to go to deconstruct box. Actually, I don't need to do this. Sorry, I'm kind of getting back into the lesson here. Okay, so what we're going to do is we don't have to do that, and the reason why is because we know the area of our voxel, right? It's 19 by 19 because we're defining it here. So to figure out our current FSR, all we need to do is we need to take the area as defined here and multiply it by the amount of boxes we have in this shape here. So simply what we can do is we can go to our voxel width and depth slider. So that's the slider that controls, the size of our voxels here. So if I increase it to 30, let's say, it increases the size of our voxels. We can just go to math. We can go to polynomials, and then we can go to square. So width and depth, the slider, let's plug into the value input. That gives us a result of 900. So each of these voxels, in my case, is 900 square meters, so pretty big. Like I said, these are kind of massive structures. And what we can do now is we have our call pattern, so the amount of boxes we have. We can multiply our area by the amount of boxes we have. So we can go to sets, list length. So I'm plugging my list into my list length. That gives me 454. And now we can simply multiply the area by the amount of voxels we have. So we can go to math, operators, multiplication, and multiply the two values together. And that gives us a value of 40,000, so a lot, 408,600 square meters. So like I said, these are huge buildings. I'm just gonna, so don't worry about doing this for yours. I just need to reset that because my computer was lagging a bit. So essentially what we've done is we've come up with the max, or our current square footage, except in meters. So what we can do now is we can just group this, and we can right click this group and we can call it current area. Now what we need to do is figure out the area of our site. So simply what I'm going to do is I'm going to select the site that my mass is sitting on. I'm going to go to parameters, geometry, surface. I'm going to right click my surface parameter, go set one surface. So I'm referencing my surface. I'll right click this parameter and call it site surface. And now, like I was saying, for the most part, when you're calculating site area, it's a 2D representation of that. So we're going to stick with that kind of standard practice. So what we can do is we can go to transform, affine, project. So transform, affine, project. Our site surface will plug into the geometry input, and that's just going to project that surface straight down to our XY plane. And now simply what we can do is we can go to surface analysis, area, take our projected geometry, plug into the geometry input of area, and that gives us the area of our site. So in my case, it's 23,000 square meters. So what we will do now is we will essentially divide our area of the building by our site area, and that'll give us our current FSR. So we can go to math, operators, and then we can go to division. So math, operators, division. Current area result will go into A. The area of our flattened site will go into B. And this is going to give us our current FSR. So I'm going to go to params, input, panel. I'll take our result and plug into the panel. I'll right click this panel and call it current FSR. Now, after I'm done that, I'll just group all of these components here. I'll right click on this group and I'll just call it current FSR. So you can see that my FSR is currently 17.6. So if I had, a city planner who is reviewing my, my redevelopment package, and I was saying like, yeah, my building's 17.6 FSR, they'd spit out their coffee. It's just ridiculous. So way too much area in this building. So the question is, how can we start to chip away at this to get between that 10 and 6? And if we're going to chip away at it, how can we chip away at it in a meaningful way? So what we're going to do is we're gonna essentially, so there's lots of ways to, let's say, chip away at the mesh. So you could start to chip away at a mesh by drawing some shapes. Like, so maybe I draw a weird column like that, and I say every voxel that's inside this shape, get rid of it, and then you check and see what the FSR is like. For the sake of this class, what I'm going to do is I'm going to take almost a randomized approach to this. And what I mean is I'm just going to literally tell the computer to try to get rid of each unit individually, and then hopefully using Octopus, some interesting patterns might arise. So from a genetic algorithm, what might seem like an arbitrary random on and off switching of each unit, eventually when you let Octopus run for long enough, patterns will start to emerge, much like in nature, you know? So essentially what we're going to do to flip off each of these things is we're going to create a calling pattern. So if we look at our output of boxes, I have 454 boxes. Essentially, we know that to call these, we can call them using a true-false pattern. So if I want to, quickly give an example, so don't follow along with this, I'm just giving an example. If I were to, let's say, set sequence call pattern, the pattern by default is false, false, true, true. If I plug in my call pattern, you can see what it's doing is it's going false, false, true, true. And if I look at the units left over, this is what a false, false, true, true pattern gives me. So it's calling half of the voxels in a false, false, true, true pattern. Now, I can create a different pattern. I could, let's say, go true, false. And this would give me another pattern. So it's calling all of these columns in a true false pattern. And that's why if we look at it kind of, you can't really see it in elevation, but if you were to look at a plan, that's why you get this true, false, true, false, true, false, right? So it's kind of this repeating bit pattern. One thing that's kind of interesting, which we've touched on already, is instead of trues and falses, you can use ones and zeros. So we've all seen, like, the matrix, like it's a screen of just ones and zeros. Essentially, in basic binary, a 1 equals true, 0 equals false. It corresponds to old school, like, hardware circuit building. So instead of true, we can say 1. Instead of false, we can say 0. So you can see it's the same thing. 1 equals 0. Or 1 equals true, 0 equals false. So we're going to do this 1 and 0, but we're going to do it on a mass scale. And to do it on a mass scale, what we're going to do is we are going to go to parameters, utilities, and we're going to borrow a component from Galapagos called gene pool. So click on parameters, utilities, gene pool. And you can see what this is it's just a list of number sliders, right? But what makes it interesting for this topic is that we can double click on the gene pool, and we can change the gene count, and we can change the minimum and maximum. So for instance, if we just want to flick between zeros and ones, what we can do is we can set our decimals to be 0, because we only care about 0 or 1. No floating point values, just integers, 0 and 1. We can set our minimum to be 0 and our maximum to be 1. I'll click OK. And now you can see I have 10 zeros and ones. So I could plug that into my call pattern. And then now you can see I can just kind of play around with this pattern, right? So that's kind of cool. So maybe, you want to do something like this and just, in the future, not for this course, but in the future, you want to skip Octopus altogether and just, play around with sliders like this. But what we're going to do is we are going to look at the amount of boxes we currently have. So I have 454 boxes. You want to hover over your box pattern. And what you want to do is you want to double click on your gene pool, and you want to set your gene count to the number of boxes you have. So I have 454. I click the little check mark, click OK. So now I mostly have zeros, so all of them are being edited away. But if I right click on the gene pool and go randomize 100%, you can see now it's kind of it's this random thing, and each of these sliders affects one unit. Now, one thing to point out is that gene pools have a certain maximum amount. I believe it's 1,000. Let's see. 1,000. 1,001. Yeah, so it's 1,000. So if you, let's say instead of, here, let's reduce my box size here. So instead of 30, let's go back to, I think it was 19. Okay, so if I go to 19, how many boxes do I have? I have 1,264 boxes. So if you have more than 1,000 boxes, what you can simply do is you can just go 1,000 for your first gene pool, go Control-C, Control-V to make a second gene pool. So this first one's 1,000. I have 1,264 items. I can double click on my second gene pool and just change the second gene pool to 264. Click the check mark, click OK. I'll hold Shift to drag this second gene pool into my call pattern. And now my input is 1,264 trues and falses. So I can randomize 100%, randomize 100%. And now you can see I'm randomly reducing all of my different units. So what I can do now is I can essentially do a little test. So I can start to use Octopus. So what I can do is I can turn off a whole bunch of these patterns. So I can, create all these random iterations of these two patterns with Octopus, and I can make sure that they fall within that 6 FSR and that 10 FSR. So that's what we're going to do first. Okay, so what we're going to do is, now that we've reduced a random amount of voxels, is we're going to recalculate their FSR. So what we can simply do is we can take our call pattern right here. We can go to sets, list length, so 652. We have our squared current area value. So that's the squared value of our voxel width and depth. And what we can do is we can multiply this value by our new called list length. So let's go to maths, operators, multiplication. So our squared value from our current area, so make sure that it's the squared value. Just plug into multiplication A. The list length coming out of your call pattern, plug into multiplication B. And this is going to give you your current area. And then what we can do is, we've already figured out our site surface. We figured out its area. So what we can do is we can again grab a division. So let's go to maths, operators, division. We can divide our multiplication result that we just got from our called units, plug that into A, and then take our site area, plug into B, and this result will be our, let's call it called FSR. So let's grab a panel again. Let's go params, input panel. And let's take our result, plug into the panel, and I'll right click this panel and I'll call it, let's call it reduced FSR. Okay. So let's group all of these gene pools as well as the reduced FSR right there. So I'm just going to group these components here. And that essentially is going to, that group I'm going to right click in, I'm just going to call it calculating the FSR of our randomly called voxel stack. Tell that sentence to your non-architect friends and ask them what it means. So does that make sense to you guys, what we did? Any questions about that? Okay, so we have our, what I called current FSR. Maybe that's better called is, maybe I'll right click this instead, call it initial FSR, because it's not our current one. So I'll call that initial FSR and initial FSR. So maybe you want to rename that too. So our initial FSR, our reduced FSR, and then now what we want to do is just list our FSR domain. So if you remember, if we look back at the Rhino file, you'll notice that the max FSR is 10, min FSR is 6. You'll also notice there's a new diagram here, and that's for probably 2 classes from now. But max FSR 10, min FSR 6. And then there's just a little, explainer there. So let's grab 2 panels to just place right here. So we'll go params input panel. I'll right click this panel. I'll call it max FSR. I'll write 10. I'll just go Control C, Control V. I'll right click this. I'll change the title of this panel to min FSR. I'll set that value to be 6. And now what we're going to do is we're going to first create a set of rules for Octopus that literally is just a true or false. It's saying iterate through data and just make sure it falls between FSR 10 and FSR 6. So make sure that it is doing that. Now, so in order to do that, let's just simply create a Boolean test. So how we do that is we can go to maths, operators, and we can go to, let's go to smaller than. So maths, operators, smaller than. And our first test we're going to set up is our reduced FSR. So our current FSR. Let's plug into the first number. We're saying, is our current or reduced FSR smaller than or equal to our max FSR of 10? So let's plug 10 into our second number. And you can see if we look at our equal out, it says false. We also need to make sure that this FSR is bigger than our min FSR. So we can test for that as well. So let's go to maths, operators, larger than. The first number, again, is going to be our reduced or current FSR. Plug that into first number. The second number is going to be our min FSR. So let's plug that into second number. So we're asking, is our reduced or current FSR larger than our min FSR? 6. So the answer here should be true, or equal to equals true. So we need to satisfy both of these conditions. It needs to be smaller or equal to 10 or larger and larger and equal to 6. So to create a Boolean and, we can go to maths, operators, and then we can go to gate and. So Boolean conjunction. And simply what this means is in order for the result of this and to be true, both of these values need to be true. So we have a false, plug into A, we have a true, plug into B, the result's going to be false because it doesn't meet both conditions. So let's group these Booleans, and we'll just call this is our current FSR we can say greater than or equal to 10 or less than and equal to 6. So that's what we're asking right there. Okay, so once we have that, we can start to set up Octopus. So what we are going to do is we are going to go to params, utilities, and you'll see Octopus sort of pops up below Galapagos, and it kind of looks like a more, I guess, a version of Galapagos that has more genes. So let's grab the Octopus component, put it on the canvas, and it's going to look kind of similar to Galapagos in that it's pink. It's also going to work similar to Galapagos in that it is going to drag out of a component instead of dragging in, right? So if you remember back to the Galapagos class when we were determining our maximum footprint, essentially what happened was you would drag out from Galapagos instead of in. So Octopus works the same way. It has two inputs, so it's genome / parameters, and then also the objectives that it searches for. So you can think about this as the same as genes and fitness in Galapagos. So the genomes is going to be the genes, and then O, the objectives, is going to be the fitness. So for G, we currently have 2 gene pools, right? So it's these 2 gene pools right here. You might just have one. But what I'm going to do is I'm going to click on the little G in Octopus. I'm going to drag it out, and I'm going to attach it to my first gene pool. So now you can see I have this little fuchsia arrow line dragging all the way out to my first gene pool. Now to attach to my second gene pool, I'm going to hold shift so I see a little plus icon next to the little DNA helix right there, and I'm going to drag out while holding shift, make sure this plus icon's still on, and then I'm going to release and make sure that it is connected to both of these gene pools. Now the second thing we have here is multi-objective search and optimization. So these are essentially going to be the fitnesses, and essentially what we're going to do is we are going to attach this to multiple things. So just want to confirm there. We are going to attach this to essentially the conditions we need to meet. So there's a few things we can do. The first condition we're going to meet is this this Boolean here. So is our FSR lower than 10 and greater than 6? And if we drag it out to our result here, you'll notice that Octopus is kind of finicky with what it wants to snap to, especially for bigger components. So there is a point where you can snap, but it feels like it's snapping to the input, so I'm not exactly sure how it works. So what I like to do is I like to just grab a little parameter and stick it on to the end. So what I mean is for our gate and, the output's a Boolean, so we go to params primitive Boolean. So again, that's params primitive Boolean. Take the result out, plug into Boolean, and then you will find that if we take our objective, it will attach to that Boolean there. The other objective that we're going to attach is our reduced FSR. So this reduced FSR will come more into play in the next class, but one thing you need to know about Octopus is that in Galapagos, you can set the fitness to either optimize towards a minimum or a maximum. So if you think about what we were doing before, we had the offset of a certain shape, and we were increasing and decreasing its offset until the difference between its area and the maximum site coverage was minimized, right? So we were optimizing for a minimum. Octopus always optimizes for a minimum. So as a result, what it's going to do is it's going to try to reduce our FSR down to 6. But in the meantime, it'll also give us some variations that are closer to 10. When we come back into this next class, we'll introduce a solar shading aspect to it, which will sort of balance out the scales a little bit more. So in this class, we'll kind of find that it'll skew towards minimizing the FSR, but we need to include this FSR calculation because that is a goal. So again, we're going to probably have a hard time snapping to this panel, so why don't we just go to params, primitive number, put a number on the end of this reduced FSR. So this is the reduced FSR. We can right click it and call it reduced FSR if we really want to be redundant. And what we can do is for our objectives, we can hold shift to see so hold shift. Come on. What's going on? Okay, hold shift. I don't know why it was being strange for me. Hold shift until you see the little arrow with the plus sign and drag it to the reduced FSR. So now we've added these two objectives. So we've added a Boolean, we've added a number. The final kind of objective that Octopus can intake is a text. And essentially what this will do is it'll create a legend. So what we can simply do is we can create a panel and we'll right click this panel and we'll just call it Octopus Legend. Right now we only have one value going out, so these Boolean, you can think of them as triggers. They're not really a value, they're just a limit, right? So we don't need to add in the legend. So the only value we really have going in right now is FSR. So let's add just one legend, call it FSR, click OK. I'll right click on this panel and go multi-line data because next class we'll add another value here. That will be the shade percentage. And what we're going to do is likewise, because Octopus is kind of finicky, we're going to go to params, primitive text. Take this panel, plug into text. And then in our output, or our objective, we're going to hold shift and drag out from our objective output and plug into text, holding shift, so we make sure to add it. So right now what you should have is Octopus, and it is starting to look like an octopus, lots of wires dangling out of it. It's connected to the Octopus Legend, which has text, which is one FSR. It's connected to this Boolean, which is essentially like a limit switch. And then finally, it's connected to our FSR, so our reduced FSR. Its phenotypes, or rather its genes are connected to our two gene pools. You might have one gene pool if you have less than 1,000 voxels. And that is it. That's how it's connected. Now, the other input here is a phenotype, and essentially that's just geometry. And you don't really need to put that in. I mean, you can, but it slows down your computer. So what you would do is if you want to see previews of the iterations, you would just plug your mesh into phenotype, but we won't worry about that now.